Okay, thank you very much for being here. I'm very excited to present to you this talk, which is about engine swapping to spatial audio plugins and how I thought it was going to be much easier than it was, and hopefully transfer some of the lessons I've learned. So a little bit about me. My name is Domenico Stefani. I did this as part of my current postdoc work. Earlier, like last year, I finished my PhD, which was more on deep learning inference for real-time audio in plugins and then embedded devices, more for like information retrieval, and I had to take a break from that. So I had a great opportunity to work on different stuff, in this case, audio plugin. I've been programming for a while with JUCE on my plugins, and I was asked by this other university, through my supervisor, to work, if possible, on some of the plugins they were using. These are open source plugins for spatial audio. This was in collaboration with the University of Parma, which is has a lab with Professor Farina, which is a big name in input response measurement. And he's now dealing with spatial audio. And what they're using is something like this one. Okay, these are open source. Not all of them look amazing, but they work really good. And the first one is a multi-channel convolver. It's very optimized. It's very good. It does multi-channel input and output for this convolution. It loads matrices. And they were using this for many purposes, like reverberation. They were doing binaural renderings, and many from ambisonics or other things. And they were using also this other plugin from the Aalto University, SPARTA suite. This is 6 degrees of freedom convolver, which loads matrices of inputs responses, and it's meant for spatial audio rendering of a scene, for example, like a real acoustic scene, for example, like this room, where you take multiple measurements of ambisonic input responses, and then you craft these sofa files where with the plugins then you can feed a mono input signal and then move, with the parameters, move the player around the room in 3 degrees of freedom, like as movement, and also you get rotation for free with ambisonics. So I was basically asked to do some kind of engine swap, what people sometimes do with car. They take a big engine and put it in a small, light car. As it happens with those things, it's not always easy because you end up having things that don't match. So it was really something like that, because the SPARTA was really good with this 6 degrees of freedom navigation, but the engine was was only mono input and also not as optimized as the other one. And so my expectation was, well, I don't know much about spatial audio, but this will be like an easier job where I can take the engine from one plugin, take the UI from the other, throw away the rest, and mix them together. In reality, this was much more complicated, as matching them was not as easy as throwing away some of the parts and gluing them together. The real reality, which looks now very obvious, is that big part of that was reading code and learning how really to read code. Not only these plugins, but also other plugins, what other people did, and how to replicate some of that. What I learned from the beginning, well, checking some of the documentation and also speaking with these researchers that were using this, was that these are very different. MCFX convolver does n times m convolutions, so many inputs, many outputs, but it can be different configuration, ambisonics channels, many things, but only with one matrix at a time. It's meant for that. It reads these matrices as WAV files, while SPARTA reads K matrices measured in, for example, a room, only mono input and many outputs that can be, again, ambisonic channels. So it reads SOFA files, which are more complex because they contain metadata on where, for example, these input responses are measured. Other big differences, MCFX used non-uniform partition convolutions, which are very optimized, also hard to handle. The other one used uniform partition convolution, which is less efficient at times. And also, the first one was not meant for really swapping these matrices live, while the second was really meant for that. It was meant to move around. So when you move around and you get closer to a point where a different input response is measured, you switch to that one in a soft way, let's say. But really, from reading the code, I understood more. I understood that on the first plugin, which was not meant to change IR matrices, really the code was let's say, following these rules. So there, it was not. It was stopping the audio callback when you change the matrix because it was not a requirement of that to change matrix live. Also, it was handling many threaded convolvers at the same time with different size partitions. Well, the second one was really meant for matrix swap, but it was for introducing, for example, a one buffer delay for position change that I understood only from deeply reading the code, because there was not a lot of documentation on this open source project. Also, it was doing crossfade, which was, however, deeply embedded in the old engine. So I crafted a little bit of a roadmap of the step I wanted to follow to integrate this engine into the other plugins. So the first, I wanted to do a very simple integration where I keep the same constraints of the first plugin. I do only one position with one convolver, and I don't move anything, but integrate it into this SPARTA plugin. Second, I move to, I replicate this for every position. So I have multiple convolvers that do the same thing for different positions in a room. And then, only then, I can switch to something that looks more like the final product, where it's more efficient. First part looks very easy because it seems like you take a plugin, and it is conceptually easy, but it's where you figure out all of the small issues, like CMake issues, incompatibility between JUCE versions, and also the need for equivalent like WAV and SOFA files to test really that everything is working right. But when this was working, I switched to one multi-position, one convolver per position, and it worked amazingly. It killed RAM because I had many convolvers with many partitions each loaded in RAM at any time, and I decided to load the biggest SOFA file, so it took 10 minutes to load, but then everything was working. And then it stopped working. It stopped working, and I couldn't figure out why. So I started reverting changes, rethinking life choices, many things. It turned out it wasn't even my fault. It was the ambisonics rotator that I hadn't even changed. And you learn about these things when you work with this open source project that do not have many documentation files, that don't have a lot of documentation, is that there were issues when you don't have even multiples of 2 as buffer size. Something stops working instead of sound embed. So figured that out, switch to efficient multi-position convolution. So yeah, at this point I wanted to have something very clever, longer convolution, longer crossfades between positions, so it can feel really like smooth, and it ended up being not needed also. Something that sounded cool from the development side was not needed as a requirement, because really these people wanted quick changes and very minimal crossfade. To give the illusion of reality when you use this in a VR system, for example. More steps, well, of course, at that point, crossfade was needed, and I had few choices. There was a talk earlier today about how to remove some FFT calculations on when doing crossfading. So doing, for example, crossfading in the frequency domain, and that was something I thought about, but really, I was dealing with all this code and making modifications to this, and I saw different versions that were going quite far from the original project. And then if you have to deal with those, the code looks really different, and really it's hard then to maintain them as separate. So I wanted to do something that had minimal modifications and while still working. So it can be more optimized. Very optimized can be like integrate all of the convolutions into a single convolver object, even when you're switching from one position to another, and then do that swiftly. Or the other solution is to have 2 convolvers, and when you need to switch, you start doing both convolutions, and you quickly crossfade between the outputs. That's less optimized, but it felt like something that could be maintained much easier. So I went for that with a simpler swap. yeah, that was I think a good choice, because when I went back to the code, really everything could be divided, and what I experienced earlier when dealing with all of these other plugins and C code was that really when you integrate different behaviors into a single piece of code, it starts being hard to really separate them when you want to upgrade one part. I should be done at the point, and there were still clicks. Crossfade is quite a simple task, so I understand why this was happening. So I really went and looked at the code and looked at the audio output, and I discovered how clicks were happening 512 or 1024 samples later than where they were supposed to happen. As I figured out, this ended up being a problem with tail partitions buffers. So I'm running like very, very early. I was supposed to take much more, and that's because I forgot to mention something. The way that these two plugins do convolution is that they all do this in real time with, say, 0 latency on the first buffer, because they take input responses and they partition them into partitions that are, in the case of the less efficient one, let's say, as big as an audio buffer, which in the case when these are used in VR applications, for example, with an head tracker on headphones, it means the audio buffer has to be very small to give the illusion of realism. So you're wearing a headset, for example, you're moving around the room, or in the case of the headset, you're really moving in a small space. For example, in I don't know, car speaker simulation, you're moving just a little bit, but everything is changing, and to give the illusion of realism, everything has to happen very quickly. So audio buffer is very small. When doing partition convolution with an equivalent scheme and a uniform scheme, all the entire input response is partitioned in this very small buffer sized blocks. It means we get many partitions. What happens is that CPU is not super optimized to deal with a small number of operations and many of them. What happens instead in non-uniformly partitioned is you cut only the first partitions to that very small size, and then you double in size. And then at some point you double in size again. So you end up having the first partitions being very small, so you can have your low latency. And when you gather enough audio that you can really convolve with a bigger partition, you convolve with a bigger partition, and you get all the optimization you can get from doing more parallel operations. It ends up that, however, this non-uniformly partition like scheme is much more hard to handle. You can have, like in this case, many threads that compute all these different things at different times. And so what happened at that point was that when I was switching to a new position, the new convolver that I start using now doesn't have a context of the audio that was happening. So I need to fill the buffer. And that's, of course, something not as hard, but also you need to figure out at that point how much to fill this, because there's all these different partitions. They're all running at the same time. So it depends on the size of the partitions, also on the length of the whole impulse response. So it wasn't something that I was doing properly, because I was following what the old plugin was doing. And however, I couldn't use the convolver, let's say the crossfade algorithm from the old plugin, the less optimized one, because it was so much integrated within the code that I couldn't really separate that. That was the reason why I decided to go with something that was more like two pieces and not a single piece of code. And that was good. That started working after that, and very happily after testing, I was able to deliver this whole plugin. I didn't go over the the whole UI part, but there was something else obviously about that, because non-uniform partition convolution have more parameters. You can decide how big, of course, the first partition is, but also the largest one, because there are trade-offs in different architectures on how optimized that can be. This is an example of an amphitheater that gets simulated. The UI is not amazing, but it was like that. I didn't change that. An amphitheater where there's a single source, and the player can move around and rotate around there, and metrics get switched. The way I ended up testing this, and I found useful for myself, was to use a DAW. For me, it was useful to use Reaper, where I could easily automate all of the parameters that were triggering code changes or code calls that I knew I was writing, so they could like trigger an error or cause the audio to have issues. It ended up being very good. It ended up being 2 to 3 times faster with 2-second IRs. And if you go to longer IRs, it can only get better, because that's how non-uniformly partitioned convolution works. With smaller input responses, of course, you don't get as much. But still, even with the same size, gets more into the complex, but even when in the situations where the non-uniformly partitioned convolution algorithm behaved like the other one because of the way the buffer size could be set, the new one was more optimized. This was instrumental in helping these researchers use more instances at the same time. In fact, first call, why they called me was, can you add with this new engine, can you add multi-channel input? And I'll need a little bit more of like coding time to add that, but basically what I added with this way was the ability to have multiple instances with much lower CPU load and have them on the side on the same computer. For example, to emulate a 2-speaker system instead of a single mono input. Last thing, the way it ended up being very useful to me to test and to find out about errors in the code and how my code was influencing that was, I ended up using the Reaper configuration I showed you before, and like sending audio through and recording, automating different things, changing the code, and then recompiling and running through and taking a lot of notes. And one thing that I think people can replicate back home is how I ended up solving these issues in the end, was that at this time I was very lucky to be hosted in Stockholm in an office full of great audio developers, very knowledgeable, some of them are here, and they were all very busy, so I didn't want to bother them. And what I did then was I thought to myself, well, if I want to go to one of them, I want to really have like a very concise question and solve all of the stupid things myself. So I was taking a lot of notes, and I was trying to prepare a discourse to have with the person, and I was trying to take away all of the simple things I could solve myself. And it ended up being something very similar to rubber duck debugging, if you know about that. And I think it's very useful. People can use that themselves without anyone else around. Try to simplify a problem and describe it to someone, even in your head, and try to minimize the number of questions you have for that person. That ended up being very useful. So that's it for me. Thank you very much.